All right, we're going to start in on the next section of chapter 10, which talks about a little bit more about chords. We learned these in the first day. They're the segments that go from one edge of a circle to the other. Now we're going to talk about how to kind of use these with some of the other parts of a circle. So the first thing we have to talk about is what we call an arc of a chord. So whenever we create a chord, so in the picture below here, you see that we have a chord that goes from one side of the circle to the other. So maybe we call this chord AB. Well, when we create that chord, what ends up happening is it creates what you see here as an arc in red, and it also creates a second arc that goes the other way in green. So remember that arc is just the unbroken part of the circle. But when we talk about the arc for a chord, what we want to focus on here is it's the minor arc. It's the shortest route from one point to the next. So no matter where the chord is in the picture, we want the shortest route from one point to the other. So the minor arc in this case is the one in red, where we're looking at from A to B. Green is also an arc, but it's the longer arc, which is not what we want in this particular instance. So the big thing here is when they talk about arc of a chord, when you see that phrase, the minor arc, the shortest distance between the 2 points. Now, when we create chords, and like we said, once we put the chords in, they create those minor arcs. One of the things that we have to be aware of is if the chords are congruent. So if I've got this chord here that I'm going to highlight in red with this chord over here that I'm highlighting in red again, if those two chords are congruent, then that means that the arcs they create, so this one that I'm highlighting in pink and this other one that I'm highlighting in pink, must also be congruent. So as soon as the chords are congruent, the arcs are congruent, and vice versa. It works both ways. So if I know this chord is the same as the other, and I tell you that this chord is 40 degrees, and they say find this chord, or this arc, the arc over here is the same as the arc over here, so x would equal 40 degrees. So if we know the chords are the same, the arcs are the same. If the arcs are the same, then the chords are the same. It works both ways. Also then, because arcs and angles are the same, that means that these angles in the middle would also have to be the same as well. So it kind of all goes hand in hand. Angles are the same, means the chords are the same, means the arcs are the same. So it's just a lot of setting things equal to each other. So for an example, if we look at this problem here, it says find the measure of arc DE. So we want to find the measure of this arc right here from D to E. Now, anytime we're trying to find something in a picture, typically we label it with a variable, so maybe we call this x. And what we have to understand here is if I go all the way around the circle, so whenever time we go all the way around the circle, we have 360 total degrees. Well, so they've told us that in red here, this arc is 30 degrees, but what else we notice in the picture is that they're telling us this chord AB and chord BE and chord DE are all congruent. So we have to see these little tick marks on each of those chords. That means that all of the arcs that go with it, so arc AB, arc BE, and arc DE all have to be identical. So whatever DE is, so does BE have to be, and AB would also have to be. So basically what we're looking at here is all four of those arcs. So we have four different arcs making this circle have to add up to 360. So I've got 3 x's plus a 30 degrees they gave me has to equal 360. And now I can just solve my regular equation. So I subtract 30 from both sides. 3x equals 330. And then if I divide both sides by 3, x would be 110 degrees, which is what we wanted. So anytime we see congruent chords, we can use that to then put the arcs congruent to each other as well. A theorem that we're going to utilize here talks about the fact that if chords are the same distance from the center, so if I have two chords, so in this case we have chord AB and we have chord ED, and we're looking at the distance from the center, so ZC and XC. Now these distances are going to be perpendicular because anytime we talk about distance from a point to a line, it's perpendicular. And so what we're saying here is if I know this distance from the center is the same as this distance from the center, so if those two pieces are identical, then that means my chords have to be identical as well. So AB and ED have to be the same length. And so what that might look like is they might say, or given a picture, they might say ZC is 4, XC is 4, AB has a total length of 10, and they're asking what is the total length of ED. Well, since both chords are exactly the same distance from the center, that means this X would have to be the same as this 10, and so X would equal 10. Or they could work it the other way as well. They might tell you first that the chords are the same, so maybe they tell you AB is congruent to ED, and then they want to know if ZC is X and XC is 12, what is X? Well, that means these two pieces must then be the same as well. Also, if we extend back to what we just learned, if the chords are exactly the same, so if ED and AB are exactly the same, then that means arc AB and arc ED are the same. So this section is kind of nice in that most everything is just like everything's equal to itself, or everything's equal to each other. So it's really straightforward stuff for most of the types of problems we're going to see. And so if we look at a quick example here, it says what's the measure of CT? So they want to know the chord CT, and they want to know the measure of arc CA. So notice in the picture, chord CA is the same distance away as chord CT. So this chord CA and this chord CT have to be identical. So then for the first question, CT must be 42. Those two chords have to be identical because they're the same distance from the center. Likewise, if we're looking at the measure of the arcs, if the chords CA and CT are the same, then arc CA and arc CT are the same. And so if they want CA, that's got to be the same as CT, which means it's 124 degrees, no work involved. So if we're the same distance from the center, the chords are all going to be the same, the arcs are all going to be the same. So it's just a matter of setting equal and then solving for whatever's left. Now the last type of problem is a little bit trickier, and so the picture's already kind of filled in here for you, so we're going to kind of talk us through it. So what's going to happen in these problems is we're going to have a line coming out of the center. And so that's one of the first things that we have to be careful with here is a segment passing through the center. Now if that segment is perpendicular, makes the right angle with a chord. So I'm going to highlight the chord in a little bit different color here, so let's go purple. So here's my chord DF. So I've got a segment that I highlighted in blue. It comes out of the center and is perpendicular to my chord, which I highlighted in purple. When I see that situation right there, what's going to happen is my chord gets cut in half, and as well as the arcs then, because if the chords are the same, the arcs are the same. So this segment CE in blue is going to cut everything it touches in half. And so that's when it comes from the center and is perpendicular to the outside. Now, if we look at the problem that they give us with this scenario, it says if DF has a total length of 16. Now we just said DF is going to be cut in half, so that means this top piece would be 8 and this bottom piece would be 8. The diameter of the triangle is 20 meters. It wants the distance from the center of the chord. Now here's the thing. The center of the chord is right here that I'm highlighting in purple now. So I need to find that length given the problem that they told me. So notice I have this, I'm going to highlight this in a different color so it stands out. I've got this half of my chord that's perpendicular to the piece of the picture that I want, and it forms a right angle. So if I can connect those two endpoints here, we create a right triangle, and that right triangle's hypotenuse is the radius of the circle. And so when I set this up, it's going to be the same setup every time. I'm going to get this right triangle set up, and I'm going to have two of the values, and I need to find the third, which means we're going to use Pythagorean theorem. So in this case, they actually told us that the diameter is 20, which means the radius must be 10. And so if I want to find x, the C value is my hypotenuse, or 10, so I take x squared plus 8 squared is equal to 10 squared. I'm using Pythagorean theorem for my right triangle. And then if I use my calculator, I can subtract 10 squared minus 8 squared, and I get 36. If I take the square root of both sides, x would equal 6. And so there's my length from my center. So in these types of problems, you're always going to go ahead and set up that right triangle. So if I kind of get rid of a lot of this stuff in here, no matter where they put the problem, so maybe they put this line out here and a chord that's perpendicular out here. So now we're looking at a situation like this. No matter how it goes, as soon as I see that perpendicular right here, I want to draw in a radius, and now I have a right triangle that I can set up and solve using Pythagorean theorem. So it's always going to be the same type of process every time when we're working with that type of situation. Now with that, you should be able to complete the worksheet from class. So you either need to get that from us or get it off of Google Classroom and work through as much as you can, ask questions in class or email, or access the answer key as it becomes available to answer any questions that you might have.